Well then, we are back. So let's continuing discussing um, on this topic of RPY angles. Um, so on the last video, which was the part 3, so I released I divided in 3 parts. So on the part 1, it was kind of a introduction to the RPY angles. And on the part 2, um, I explain how you can construct these matrices, or it was on the part 1 that I explain how to construct these matrices, which is basically the characteristical matrices of rotation above the axis x, y, and z. And what we have to do is a analysis and see in which direction of the reference frame or the framework, in which direction this axis is pointing, doing a relation to the other reference system. So we saw that A was pointing on the same direction as Z, and on the part 2, I think we discussed the inverse kinematic solution of RPY. So we apply the inverse, not only the inverse, but also the forward. But right here, I think we just have applied the inverse, which is where we wanted to set our links and joints on the 3D space that is this robot is on it. And doing the inverse kinematic analysis, we use inverse transformations. So we solve the transformation equation. Then we obtain a equation more simple, and we solve for the angles of phi A, phi O, and phi N, which is respectively the angles of rho, pitch, and yaw. And perfect, right here, these angles it gives us the orientation of the robot, of the joints, of the links. And it's about time we are starting to work with the simulations. And on the on the last video, on the part 3, we saw very briefly, very quick, 2 simulators that we can use, that you can use to do your studies in robotics. And on a real situation, when you got a hardware, the robot, and a controller, you can apply all these theories, these techniques, all these concepts. And if you wanna work with, let's say you got a nice hardware and you have to transform all these concepts in algorithm, so this is going to help you. So we saw for the angles, and today we will start to solve examples. So let's get started. I will use again the 3rd edition. We can solve for examples of the 3rd edition and the 2nd edition, and they are different as I'm seeing. but I will use the third edition. So it's going to be the third edition. Third edition. Okay. And we will solve first example 2.21. 2.21. Okay, and the statement is very short, so I can just write. So, and again, in robotics, you have to be good in text interpretation because um, we will saw a lot of terms and not only text interpretation, but also understand the terms that it's the robotics terms that we use. So the desired final position and orientation of the hand of a Cartesian plus RPY robot is as follows. So from here we can already start our discussion. As you can see, this statement is full of terms of robotics. So from here you have to be able to understand what this statement is telling, and of course it's important to know since the beginning. We start from the chapter 2 and on the concepts that we saw we will apply right here, and from here to throughout the series, throughout as we got more deeply on the book. Okay, so first I will write the matrix, and then we can start to interpret this statement. Okay, and we already start with a transformation, and what this transformation it means. The desired final position and orientation of the hand of a Cartesian and RPY robot. So I can write is the transformation of course is the p-frame in relation to the R frame. Now it's up to you. What is the P frame and what is the R frame? Well, P frame, see, it's all about text interpretation. P frame is the final position. The book, it doesn't let this explicit, but it's your job to do this interpretation. So P is the final position and R is from referential. So is the transformation of the final position in relation to the reference frame. See, we start interpreting the text, and if you have a figure, a robot draw it, we can interpret this figure, this draw, and from here we can start to write our matrices or transformation equation. But here he gave it to us these matrices, and the content of the matrix is the representation of the motion of the robot or the position in which this robot is on it, the initial position. So, okay. And next, and Y, and Z, and 0, and this line, this last line in the last column is the scale factor, just to maintain these matrices on its quadratic form. Okay, OX, OY, OZ, 0, AX, AY, AZ, 0, and right here its position. Oh, I said that this P is from the final position, but if you draw a robot arm, this P, it can be from the robot arm, but for me it doesn't make sense since it was not given. But if we following the book, we will get these elements, and probably this element is this frame. Okay, so that's no problem. PZ and 1. And this is equal. Now we get the coordinates. So let me write them. Two point 75, 665, 6. So this last column is representing the position, and that's it. Is the position, because on the book we also got illustrated a vector doing the analogy with the robot arm, name it of P. Okay. And now let me write the question. The question it asked us to find the necessary RPY angles and displacements. Okay, so we will need these solutions. Okay, so let me copy these solutions. We have solved it for A. I just need to copy this. The solution for the phi A angle, the angle of rho, the solution of the phi O angle, and the solution of the phi N angle. Okay, now it's easy. Let me copy these matrices to use as reference, so we can guide ourselves. Okay, so the first angle, the phi A angle. Okay, and remembering, and this is the complementary solution. Let me see, the complementary solution. Exactly, the complementary solution so phi A angle is equal A tan and ny is equal 0.113 and nx 0.233. So let's use the octave to help us. So let's see. We'll clean the octave memory. So type clear all, and now CLC to clean the command window. Now we can start. We can type phi A and DAG from degree is equal A10 2D, and now the coordinates 0.113 and 0.233, and enter. Okay, 25.87. So phi A, this is equal 25.87 87, and we can do a approximation to 26. And also we need to evaluate the complementary solution. So is minus 0.113, and right here is also minus 0.233. And again, we can call this phi a comp deck A10 minus 0.113 and minus 0.233. Let's try it again. Phi, just phi and deg, which is equal. The problem is because I forgot to type 2D, so it's okay. 2D, I think it is right now. Minus 154.13. Okay. So right here, I will just revise with you again. And you use the appendix A from this book that I'm using. And the appendix A says that if both sine and cosine are negative, so this angle is on the third quadrant. So, and this is clockwise, anti-clockwise, not clockwise, it's anti-clockwise. Because if we do clockwise, we will use 180 minus 154. And this is wrong right here, as this is anti-clockwise. And here is clockwise. And if it was clockwise, so it will be 108, but as this is anti-clockwise, so is 306 minus 154, which is equal 206 degrees. And this is the solution for the phi A angle. Okay, now let's see the solution for, and this is because we wanted to solve, we wanted to know the orientation. So the angles are given to us the orientation, and as this is a Cartesian one, as you can see on the elements of this matrix, Cartesian. And this last column representing the Cartesian, it will return to us the position. So right here we can obtain position and orientation. And the angles will give to us the orientation. Okay, now for the phi and angle. I don't give a fully interpretation of this statement, but just using this, taking the time that I comment about what this angles is returning to us, and I comment about the position and orientation, so we can use this time to do a quick interpretation. So right here we wanted to know the desired final position and orientation of the hand of a Cartesian and roll pitch in your robot. And as you can see, this first column is representing the orientation, and this last column is representing the position. And again, look how important is the interpretation. Is the hand, is the final actuator, is the end effector. Remember, we always wanted to know where the end effector is going to be at the end of some task. Okay, that was very quick, and let's continue. Now we can solve for the phi and angle. So, and that is huge, 810. Let me just copy this. And now modifying okay, so right here we have cosine of phi A, sine of phi A, and we have solved it for phi A and phi A, as we have two solutions. Phi N and phi O also will have two solutions. So right here is, let's do it, is cosine of 26, which is equal 0.9 and sine of 26, which is equal 0.43. Okay, so is A10 minus AY, let's copy this again to use as reference. Okay. So AY is equal minus 0.287 times cosine of phi A is 0.9 plus AX, which is equal 0.939 times sine of phi A, which is equal 0.43. Okay, and remembering this is y and the next is x coordinate. OY right here. OY is equal 0.951 times cosine of phi A, which is equal 0.9, and this minus OX is equal 0.255 times sine of phi A, which is equal 0.43. And this is x. Okay, so let's first evaluate this. And this is 0.14547, and I think we can do a approximation and just 0.15. And right here we got 746. Okay, phi n is equal 810 to 0.15 and 0.746. Now let's use octave and see what we get. Okay, phi n dag is equal a10 2d 0.15 and 0.746. This result is diverging from the book. Let's try the complementary solution, and we'll keep with our analysis. But we get 11 degrees, right? 0.4. But this result is diverging from the book. Let's see the complementary solution. So I will just modify this. Um, so right here is cosine of 206 and sine of 206. Degrees. And cosine of 206 is minus 0.8, again 0.9. And sine of 206 is 0.44. Right here, I think it's best I use 43. Let's see. I should do a approximation to 4. Okay, we can correct this after. Let's see what we get right here. So is okay. And right here is minus 0.9, and right here is minus 0.44. Right here is the same, minus 0.9 and minus 0.44. and this is 0.258 sorry, is minus 0.5486. Well, and right here is minus 0.743 It's the same that we get up here. Let me pass a line so we don't get confused. So I just will change the sinus. Okay. Now on the octave, I will copy this line and modify the sign of the coordinates. Let's see. Okay, now 168, 169, 169. Well, let's see. As both sine and cosine are negative, so that means it's on the angle is on the third quadrant, and what we do is to subtract from 306 the value that we got. Which is equal 199, and this value, it's also diverging from the book, and now I'm confused. And what I will do is to calculate the phi O and see what we get also. So let's do for phi O. So minus z which is equal 0.966 minus 0.966, and right here we have a comma. Okay, nx is 0.233 and cosine of phi A 0.9, and this plus ny 0.113 times sine of phi A, which is equal 0.44. and this is equal 0.259, and I'm doing a approximation. Okay, so VO is equal 810 to 0.966 and 259, and this is equal, so let's see, going to the octave, VO DAG, let's clean all this command window. VO DAG is equal 810 2D 0.966 and 0.259, which is equal approximately 75, and that is correct. Is the same result that we get now. We're getting the result that is on the book. So I don't know, because I don't know what I do wrong right here, because these two values is diverging from the book. Okay, so with these angles we got the orientation, and that's it, the end of the exercise, because the position it doesn't change, the position keeps the same. We got px, which is equal 4.24, py is equal 2.75, and pz, which is equal 6. So we finished the example. And we have to add units. And I was forgetting, we also got the complementary, or 255, which is the complementary angle. Okay. So let me try to illustrate with a figure, with a draw. Right here, this one, it works for us. We are changing this P right here. This P it's not exactly for position. It's just the name that we are given to this vector or robot arm. Okay, and what matters right here is px, py, and pz, which are the coordinates of this P. So we got the position, and with the angles of roll, pitch, and yaw, we got the orientation. And that's it. Now let's just see again the softwares that you can use just to play with, just to mess around. Okay, and if you don't understand, we will have another opportunity with more examples. Again, on BabaCAD. So let's see, we can add position, right here I'm doing a rotation, and let me see with other simulator which we are able to attach it imaginary frames. So right here I'm on Robot Decay, and this is online in very light. You can run it on your computer also. Okay. And double click on the robot body, and right here we can change its axis, the position and orientation of the joints, which will change the position and orientation of the axis. Let me place right here, double click. Let me change the orientation. Okay, let's try it. Double click. Okay. We have 6 joints. Let's one. I don't know if you are seeing my pointer, but I'm counting right here from the base 1 joint. Right here another joint, 2. Right here 3. Right here 4, 5, and 6. Let's see. We are doing a rotation, and this rotation is above the z-axis, and as you can see, the z-axis, it doesn't change right here. The z-axis, it doesn't change because we are doing a rotation above it. But yeah, now we are doing a rotation. Right here, x-axis is in red, the y-axis is in green, and in blue is the z-axis. And the other axis, I think, is the axis of roll, pitch, and yaw. I don't know exactly. Um, because as you can see, we got a reference frame, and this is the reference frame, and this is both these frames are reference, and we can also attach it on the other joints, um, on the end of the link frames. Right here, if I'm not wrong, we can write, let's see, if this is the base, we can write for this indefactor a transformation in relation of the base, and we can call this base of universal or R from referential. So we can write a transformation in relation to the frame R or U. Sorry, a transformation of the frame R or U in relation to the frame. Now we can call this indefactor of, I don't know, hand, or just E for indefactor. So is T a transformation in relation to the transformation of R in relation to E, the frame E, a transformation of the frame R in relation to the frame E. Okay, for now is all. You can use this on your browser. So try it. It's very nice, very light. And as you can see, we have more resources, more features to use. And also you can try BabaCAD, which is also very nice. Okay, that's it. Thank you.